Here are solutions to homework set number 12 for ECE 111. This week we're covering statistics, namely the chi-square test, normal distribution, and t-distribution. Now the first problem looks at random numbers. In MATLAB, I can generate a random number, so this would be a six-sided die. What this code does is this guy right here generates a number between 1 and 6. Rand is a number between 0 and 1, times 6, rounding up, gives you 1 through 6. What I do is use that to generate a six-sided die, then repeat 90 times, and I count how many times I rolled a 1, how many times I rolled a 2, and so on. So if I run that code, I'm going to get a different answer every time. This time when I ran it, I got 13 1s, 14 2s, and so on. Is that a fair die? Well, that's a chi-square test. What a chi-square test is, it takes the expected number of results. I've got 90 die rolls. The probability of each number is 1 in 16. So I should have 15 1s, 15 2s, 15 3s, and so on. I actually had 13, 14, 13. The chi-squared score, take the difference squared divided by the expected number. So this would be 2 squared over 15, 1 squared over 15, 2 squared over 15. Here is 5 squared over 15, and so on. That's your chi-squared value. Add them all up, and I get 2.8. To convert that to a probability, I can use the chi-squared table, or, probably easier, is use StatTrack. StatTrack, you can sit there and input the degrees of freedom. This is number of bins minus 1. I have 6 bins, meaning 5 degrees of freedom. My chi-squared value is 2.8, so that corresponds to 26%. 26% chance this is a loaded die. And kind of what the numbers mean, if this number is really, really big, then your data is inconsistent with the assumed distribution. I can be fairly certain that this is wrong. It's not a fair die. If the number is too low, like 0.01, I'm suspicious that I fudged the data. That isn't real data. In the middle, like what we got here, is normal. No reason to conclude that die is not fair. No reason to conclude that I fudged the data. That's problem 1. Basically, MATLAB is pretty well debugged. Its random number generator is pretty good. Problem 2 looks like a loaded die. So here what I do is 12% of the time, I always roll a 6. The rest of the time, it's a fair die. Can I detect that the die is loaded? If I have access to the source code, I can look at it and say, yep, it's loaded. 12% of the time I get a 6. Suppose I don't have access to the source code. All I can do is just roll the dice. Can I tell the die is loaded just by rolling them? So the procedure is same as we did before. Roll the dice a bunch of times. Here I roll it 90 times. Count how many times you get a 1, 2, and 3. And these are my results. So this is the number 1s, 2s, 3s, and so on. Now calculate the chi-squared score. Same as before, 2 squared over 15, 1 squared over 15, 10 squared over 15. Add them all up. I get my chi-squared value. To convert that to a probability, go to a chi-squared table or use StatTrack. What 4.53 means with 5 degrees of freedom is 52%. So I'm still only 52% certain that this is a loaded die. Basically, 12% loading is pretty hard to spot, and casinos use that. If I have an electronic gambling machine, I can load the dice, put it against you, and as long as I'm not too flagrant, it's really hard to tell. But it does show up in the long run. That's what casinos care about. They care about the long run. Short run, like 90 rolls, the customer is really not going to be able to see it. If instead I roll the dice 900 times, again, this isn't what was asked for, but just for fun, if I roll the dice 900 times instead, do the chi-squared score, I get a huge number. That says, basically, I'm just about guaranteed that die is loaded. So that was problem number 2. Problem 3 is determine whether or not you're psychic. So here what you do is you take a deck of playing cards and predict. The first card's a heart, diamond, club, or spade. Flip it over, see if you're right. Same for the second card and third card. Keep track of how many times you're right, how many times you're wrong. I tried it. I was right 10 times, wrong 42 times. The expected number is 1/4 of them should be correct. I should be right 13 times and wrong. Take the chi-squared score, 3 squared over 13, 3 squared over 39, add them all up, I get 0.92. And again, I go to a chi-squared table. To convert that to a probability, I use a chi-squared table with 1 degree freedom. I've got 2 bins, meaning 1 degree freedom. 0.92 at 1 degree freedom corresponds to a probability of 0.66. So there's a 66% chance I'm not just guessing. That's basically no conclusion. Sadly, apparently I'm not psychic. So that's a chi-squared score, or chi-squared test. Chi-squared is the test of a distribution, such as if you have a random number generator, is it really random? The next set of problems deal with a normal and a t-distribution. So the problem we're going to look at is I'm going to roll a bunch of dice. I'm going to roll 6 4-sided dice, 5 6-sided dice, 4 8-sided dice. And in MATLAB, I can do it like this. I'm going to roll 6 dice, times 4 rounded up. These are 6 4-sided dice. This is 5 6-sided dice, 4 8-sided dice. Take the dice, add them all up. One way to determine the distribution is called a Monte Carlo simulation. I toss the dice 100,000 times and count. How many times I got a 1, how many times I got a 2, and so on. The result looks like this. That's the central limit theorem in action. This is a bell-shaped curve. The distribution converges to a normal distribution. With Monte Carlo, I can answer questions, like what's the probability of getting numbers 60 and higher? Well, to do that, I can just count. How many times did I get the numbers 60 to 90? Divided by how many times I rolled it, it's 8.5%. If I want to know the 90% confidence interval, I want to draw these two thresholds. Here, the left side has an area of 5%. The right side has an area of 5%, leaving 90% of the middle. What are those two thresholds? And again, using Monte Carlo, I can just do a search. Let's sum up all the data, all the results between 1 and 40. I get 6%. 1 and 39, 4.6%. So somewhere between 40 and 39, call it 39.5. That's the left tail. For the right tail, how far do I have to go to capture 5%? 61 to 90 is too much. 62 to 90 is too small. So it's between 61 and 62. Call it 61.5. So that tells me the 90% confidence interval is 39.5 to 61.5. That's the beauty of Monte Carlo simulation. Knowing nothing about statistics, I can tell you probabilities. The cost is I had to roll the dice 100,000 times, and if this is an experiment that costs $10 per experiment, I just shot $1 million. So that's not always the best way to go. Problem 5 uses the central limit theorem. Distributions converge to a normal distribution. The die roll, if I use a normal approximation, will be as follows. The mean will be, since I have 6 4-sided dice, 6 times the mean of a 4-sided die plus 5 times the mean of a 6-sided die plus 4 times the mean of an 8-sided die. Add them all up. That bell-shaped curve that we saw, the average should be 50.5. The variance also adds. So take the variance of a 4-sided die, there's 6 of them, variance of a 6-sided die, and there's 5 of them, variance of an 8-sided die, there's 4 of them, add them all up, that's the variance of y. Take the square root, it's 6.5. So if you go left and right, these are typically like 1, 2, 3 standard deviations. This distance is 6.5. Now, well, I can actually kind of see that. If I plot my data from before, the bar graph, versus the normal approximation, that's the red line, the two match up really, really well. That's the central limit theorem. It converges to a normal distribution, meaning if I use the normal approximation, I'm pretty darn accurate. So, using that, I can find the 90% confidence interval. Go to a normal table and find out where's the tail 5%, and the z-score is 1.64485. So if we go left and right, 1.64485 standard deviations, I'll capture 90% of the area. Calculating is between 39.7 and 61.2. Comparing that to Monte Carlo, that's basically the same answer. But I got the same answer without ever having to roll the dice. That's the power of statistics. If I use Monte Carlo, I might be blowing $1 million. Using statistics, I can do it with 0 measurements. I know what the answer is. If I want to find out the probability that I'm more than 59.5, again, I take, here's the mean, here's 59.5. How far is 59.5 from the mean in terms of standard deviations? That's called the z-score. It's your 59.5 minus the mean over standard deviation. It's 1.37 standard deviations. Go to a normal table, find the number 1.37, and find the tail. It will tell you that the tail is 8.56%. So the other area is over here, 91.44%. Again, that matches with Monte Carlo. Monte Carlo was 8.57%. Here it's 8.56%. I basically got the same answer with 0 trials. That's part of the power of statistics. Problem 6 says, suppose I don't know the mean and the standard deviation. If I do, I can use the normal approximation. If I don't, what I can do is I can collect some data. From the data, find the mean and the standard deviation and use that. This is a slightly different distribution. This is a t-distribution. The t-distribution is probably the most important distribution you'll ever see. It looks like a normal distribution. It's got a mean and a standard deviation. It's got the same bell-shaped curve, but it takes sample size into account. So suppose I do that. I'll roll the dice 4 times, and you're going to get different answers every time you roll it. It's random. This is what I got. I've got a mean and a standard deviation. Now, to find the 90% confidence interval, I want the left tail to be 5%. I want the right tail to be 5%. I need to know what the t-score is. How far out do I have to go so that the tail is only 5%? That's a little bit different than a normal distribution. I've got 4 data points. The degrees of freedom is sample size minus 1. Basically, a single data point tells you nothing. So if I have a single data point, the degrees of freedom are 0. I need at least 2 data points. With 4 data points, I've got 3 degrees of freedom. From a t-table, 5% tails and 3 degrees of freedom corresponds to a t-score of 2.35. So we need to go 2.35 standard deviations out. So this is my confidence interval, my 90% confidence interval. I should roll the numbers from the mean plus or minus 2.3 standard deviations, or between 32 and 72. And that's pretty close to what the Monte Carlo result gave, actual results from Monte Carlo. A little bit wrong, but then I only have a sample size of 4. So it's actually not too bad considering my small sample size. The probability of getting numbers bigger than 59.5. Same thing. I've got the number 59.5. I want to know how far is that from the mean in terms of standard deviations. So that's called a t-score. It's 0.81 standard deviations away. From a t-table, I've got 3 degrees of freedom. T-score is 0.81. The area of the tail is 23%. It should actually be 8%, so it's a little bit wrong, but again, I only have 4 data points. If I collect more data, in this case 10 data points, repeat, I've got a mean, standard deviation. Now, with 9 degrees of freedom, meaning 10 data points, with 9 degrees of freedom, 5% tails happen at 1.833 for the t-score. So go left and right, 1.833 standard deviations. Pretty close to what the actual answer is. If I want to find the probability more than 59.5, I find out what the t-score is. It's 1.2 standard deviations away. Go to a t-table, 1.25 standard t-score of 1.25 with 9 degrees of freedom has a tail of 12%. Should be 8.5. Again, a little bit off because they only have 10 data points. So that's homework set number 12. It's probably a little bit confusing, but hopefully you can see what the power of this is. If I don't use statistics, I can always use Monte Carlo. But if it costs me $10 for every experiment I run, I'm going to blow $1 million. With statistics, I can get answers that are almost as good using far fewer than 100,000 die rolls. Just 4 die rolls work pretty well. 10's better, 20 be a little bit better. Once you get past 20, there's really not a lot of point. The data is good enough. 20 is almost the same as infinity. So with statistics, I can save a lot of money and measurements. That's important in industry. If I want to know what my product is coming off the assembly line, I've got to take measurements. If I measure everything, I know what my product is, but I'm bankrupt because everything's been used. I have nothing to sell. If I measure nothing, I don't know what I'm selling. I need some data. With statistics, I can actually get pretty good measurement of what's going on with just a few measurements, like 4 or 10. So that's homework set number 12. Again, this topic is kind of confusing. First time's always the hardest. But you'll get this again when you take random processes. You can actually major in statistics. So homework set number 12.